Okay, they tell us within a chemical compound generally where electrons are located within that compound. Okay, we know that in an ionic compound or in an acid, we should have an overall neutral charge, right? One of these atoms needs electrons, one of them has electrons to give, right? So we're going to talk more in our next chapter about how they can share electrons or how they can trade electrons, and that will help with oxidation numbers just a little bit. But what oxidation numbers do is they give the general distributions of electrons. This is an E with a minus. That's how I abbreviate electrons. Sorry. Okay. So it gives us the general distribution of electrons within a compound. Okay, so within a bonded compound, it tells us generally where are these electrons located. Okay, and so there's, again, some sets of rules that we can follow to help us determine the oxidation numbers of each element within a compound. Okay, and once we start looking at two-dimensional and three-dimensional structure of compounds, this will make a little bit more sense as to how our electrons are distributed when things bond, right? They can share electrons or they can trade electrons. But this gives us an idea as to which of our atoms are kind of like hogging the electrons, or which one is more likely to give it away, things like that. Okay, that's what we're talking about with oxidation numbers. Okay, so there's some rules. See, you can see these rules listed underneath there. I'm going to give you the abbreviated version of these. They have 8 rules. I don't have quite that many. As to how we find oxidation numbers of elements within a compound. Anytime we just have a compound with an element only, right? It's single element. Okay, so elemental atoms or elemental compounds have an oxidation number of 0. Okay, so this would be if we were just looking at sodium, or if we were looking at an oxygen gas molecule, or if we were looking at a molecule S8, right? Those are all single elements, so they have an oxidation number of 0, which means electrons aren't distributed unevenly, right? Oxidation numbers kind of tell us where our electrons are located, where are they pulling toward, and in elemental atoms or elemental compounds, or however you want to say it, things with only one type of atom, they can't be pulling unevenly because it's the same type of atom, right? Every sodium atom wants electrons just as badly as the next one. Or every sulfur atom treats its electrons exactly the same. So there wouldn't be an uneven distribution. Does that part make sense? Okay, so rule number 2. Fluorine has an oxidation number of -1 always. Okay, so these are kind of some things we need to think about generally in terms of oxidation numbers and generally in terms of electron distribution. Fluorine is what we call the most electronegative atom on the periodic table. Has anyone heard the term electronegativity before, or electronegative? Okay, what electronegative means is how badly it wants to take electrons from someone else. Okay, so fluorine, look at fluorine's position on the periodic table. Okay, it's in group 2. And how many valence electrons does it have? 7. So how many does it need to complete its shell? 1, right? It only needs 1. Hydrogen and helium don't really want to give or take electrons all that badly, right? Hydrogen has 1 to give and it gives it away really quickly. But fluorine wants to take them, right? Helium already has 2, so it doesn't care to take anymore. Hydrogen wants to give it away rather than to collect another one. So the atom that wants to take electrons more than any other atom on the periodic table is fluorine. So fluorine trumps every single element in terms of who gets to take those electrons. Okay? So fluorine has what we call the most electronegative atom. And then on the periodic table, as you move toward fluorine, that's how your atoms kind of go. They get more electronegative as you move toward fluorine. So elements that are close to fluorine on your periodic table are going to take electrons from others. Okay, so the closer you get to that, you'll kind of see. And we'll talk a lot more about electronegativity next chapter, but I want you to understand that atoms close to fluorine, they want to take electrons, right? They want to complete their shell. So fluorine wants it the most as compared to like astatine, because fluorine's outer shell is closer to its nucleus, right? Fluorine only has 2 levels of electrons, so its outer shell is close to its nucleus. Whereas iodine or astatine, right, they have 7 valence electrons, so they want another one, but it's like hanging out on the outer shell. They don't really care. It's not that close to the nucleus. Not super concerned about it. Okay, does that make sense? So fluorine has really close electrons that are close to its nucleus, and it wants one more badly. So fluorine always has an oxidation number of -1, which is always its regular charge, right? So in a compound, electrons are always going to float toward fluorine's side. Rule number 2, oxygen, which kind of is right next to fluorine there, has an oxidation number of -2, and this is only except when bonded with fluorine. Sorry, I'm trying to make it so I'm not writing over that thing there. Oxygen has an oxidation number of -2 except when bonded with fluorine. Okay, because if it's bonded with fluorine, fluorine takes it, right? Fluorine has a -1 charge. Okay. Otherwise, in most cases, oxygen still has its oxidation number of -2, which is its usual charge. Okay, so there's 3 big exceptions, or 3 big elements that we need to pay attention to with oxidation numbers. Fluorine is one, it gets to keep its charge. Oxygen is the next one, it gets to keep its charge. And hydrogen is the third. Okay, so next rule is hydrogen has an oxidation number of +1. Okay, the only exception to this is except when bonded with a metal. Then its oxidation number becomes -1. So almost all the time, hydrogen's going to give up its electron, right, to whatever it's bonded to, except if it's bonded with a metal. Then it kind of takes over that extra electron. Okay? So those are our 3 big elements that we need to pay attention to in terms of oxidation number. Fluorine's always -1 all the time. Oxygen 99% of the time is -2. Hydrogen a lot of the time is +1. Okay? So they get to keep their regular charge. Okay? Okay, next rule here is that oxidation numbers, like charges, must add up to, actually I'll just kind of put it like this, must add up to the charge of the compound. Okay, so the oxidation numbers of each individual element put together have to add up to the charge of the total compound. So if the compound overall is neutral, what does our oxidation number need to add up to? 0, right? If our charge is -1, our oxidation numbers need to add up to -1. Okay, that should make sense because oxidation numbers are accounting for all of the electrons within our compound, so our charge should account for all of our electrons within a compound as well. Okay, oxidation numbers are very similar to charges. Okay, and the last rule here is that the most electronegative atom, so we'll remember this is our rule for most electronegative atom, closest to fluorine, gets to keep its charge. Okay, so that's if hydrogen, oxygen, and fluorine are not in our compound, right? If hydrogen, oxygen, or fluorine are in our compound, it gives us an easy starting point. But if none of those three things are in our compound, then we look to the least electronegative atom, which is the closest one to fluorine. That one gets to keep its charge, and then we'll build from there. Okay, so it will make some more sense when we start looking at examples, I think, and I hope. But we'll try some. Okay? So those are all of kind of the rules that we need to think of. There's three big elements. What are they? Good. Fluorine, oxygen, hydrogen. Then from there, we need to understand that the most electronegative atom gets to keep its charge. Okay, from there. All right, let's try one. So we need the oxidation numbers of each element in this compound. Can we name the compound first? Uranium 6 fluoride. Uranium 6 fluoride. Good. Where's uranium? Oh, yeah, 92. There we go. Yep. Uranium 6 fluoride. So is it ionic or covalent? Ionic. Uranium has a plus charge, and it's a metal. Okay, so it's ionic. All right, good. So oxidation numbers. There's no real super way to write your answer for oxidation numbers. I'm going to show you my kind of method, or how I look at oxidation numbers, and how I start to look at my totals, and how I make sure everything adds up right. But that doesn't mean this is necessarily the right or the wrong way to write it. Okay. So would we say that fluorine always gets as its oxidation number? -1. So I like to write its oxidation number up top. Okay, because they're similar to charges, they're not really charges, similar. Okay, so if there's an oxidation number of -1 for each fluorine atom, and there's 6 of them total, how many total of that side do I have? -6. Okay, and there is 1 uranium atom. Okay, and I need this to add up to what? Well, okay, I need to add up to 6, but I need total to add up to 0, because the charge of the molecule overall is 0. So that means here I need a +6, and there's 1 of them, which means its oxidation number is +6. Okay, so my answers there are +6 and -1. Okay, which is very similar to their charges, right? In this case, there's no difference between their charge and their oxidation number. Okay, so that means when they combine to form this compound, everything went exactly as it should, right? Nobody hogged electrons from anyone else. Like, everyone just did their job, right? Questions? All right, let's try another one. Let's try H2SO4. Name that molecule for me first. Hydrogens come first. What does that tell us usually? It's an acid. And what is this by itself? Sulfate, which means it's sulfuric acid. Yeah. Just sulfuric. Hydro would be if it looked like this, H2S. If this was just sulfide. Okay, so sulfuric acid. All right, so now we have we have 3 different elements to take care of this time, not just 2. So we're going to start in order of our big elements. No fluorine, but there's an oxygen. So we're going to start with oxygen. Okay, oxygen, we said, has an oxidation number of what most of the time? -2. And there are 4 of them total, so we multiply that, right? 2 of them times 4 oxygens is a total of -8. What do I need all of my oxidation numbers to add up to? My totals. I need them to add up to 0. Okay? So now I'm going to skip over to hydrogen, right? I know a rule about oxygen, and I know a rule about hydrogen. So I'm going to skip sulfur, and I'm going to go over to hydrogen. What do we know about hydrogen most of the time? +1. Okay? So hydrogen is a +1, and how many of those do we have? 2, so that gives me a +2. So what is this X here in the middle that would get us to 0, which would be sulfur's oxidation number? plus 6, right? And how many sulfurs do we have? 1. So that means sulfur's oxidation number is plus 6. Okay, which is not a common charge for sulfur, right? But that's okay. That just means that sulfur's giving away its electrons and oxygen's taking them, right? That's okay. So they don't always have to match their charge, but they can. So our answers are plus 1, plus 6, and minus 2. Okay, so these are not the answers to our problems, right? Hydrogen, each hydrogen atom has an oxidation number of plus 1. Each oxygen has a minus 2, and the one sulfur has a plus 6. Okay, what questions do we have? Okay, let's try one more here. All right, what polyatomic ion is this? Chlorite. Chlorate or chlorite? Which one is it? 8. 8. Okay, chlorate. Okay, so now the only thing that's different on this one is this guy right here. Right, what's that telling us? It's a -1, so that means our oxidation numbers this time don't have to add up to 0. They have to add up to -1. Okay, so let's start with oxygen. We know oxygen has a -2, and there's how many of them? 3, which gives us a total of -6. I need these numbers to add up to -1. So what number fits right here? Right, a plus 5. And how many chlorine atoms do I need to split that plus 5 charge between? Just 1. Okay, so that means chlorine's oxidation number is plus 5. Oxygen's oxidation number is -2. How are we feeling? Not great yet? Okay, let's try a couple more. Let's try this one. P4O10, which is called tetraphosphorus decoxide. Good. Tetraphosphorus decoxide. Okay. We know oxygen always has an oxidation number of -2. There are 10 of them. So total, that gives me a -20. Does this overall compound have a charge? No, which means my totals need to add up to 0. Okay, so that means this, or this total X right here needs to be what? Plus 20. Okay, and I have 4 phosphorus that need to split that plus 20. So each phosphorus has a plus 5 oxidation number. Okay, that's all there is to it. Do you want to try a couple on your own? Okay. So I'm going to give you this time the name of the formula. You're going to have to come up with the compound, and then you're going to give me the oxidation number. Okay, so you got to come up with the compound and oxidation numbers for each. You what? Oh, that's okay. Okay, Alexa, did you have one? GeCl4. Perfect, because germanium's a +4. Germanium is a metal, right? Even though it's a metalloid, it's got a plus charge, so it's a cation and anion, which makes it a ionic compound. So GeCl4, what did we have as our oxidation number for chlorine? Okay, -1. We had 4 of those, which gives us a -4. We need that whole thing to add up to 0, which leaves us a +4 over here, which germanium would have been +4, and chlorine would have been -1. Since there's no fluorine, oxygen, hydrogen in our compound, the most electronegative, which is chlorine, it's closest to fluorine, okay, that gets to keep its regular charge, which is -1, as its oxidation number. Does that make sense? That's right. If phosphorus was the only one in there without oxygen or whatever, then that would keep its -3. That's right. Okay? Second one, hydrochloric acid. William, what'd you have as your formula for hydrochloric acid? HCl. HCl, good. What were our oxidation numbers here? Anybody? Go ahead.
For hydrogen, it's a +1, and chlorine is a -1.
Perfect. +1 and -1. Okay, would we agree with that? +1 and -1. Okay, last one, dinitrogen pentoxide. What did you have, Haley, for your formula? N2O5. Perfect. Okay, and what about our oxidation numbers? Thomas, what did you have?
-10 for the O.
-10.
Oh, no, that's what it would be.
Yeah, so I want just the regular oxidation numbers, not the totals.
2.
So -2 and
Then 5.
+5. Good. So we need to remember that the totals that you come up with, those aren't your oxidation numbers. It's the individual atom. So whatever it is per individual atom, that's our oxidation number. So we know oxygen is a -2, which is a -10. We need this to add up to +10 because we want the whole thing to be 0. That +10 has to be split between 2 nitrogens, which gives us a +5.